So now let's talk a little bit about B trees. B tree is commonly used in a kind of block-oriented storage. For example, file systems or database management systems. When we have a huge amount of data, we won't be able to upload all of them into the internal memory because the internal memory is relatively small. So we'll have to store them on disks. And disk access is usually slow since in order to find something, we're going to have to spin the disk and to find the right track first, and then the right sector, and finally find the data somewhere. So it will be quite slow if all the data are scattered everywhere on the disk. So in order to have a faster access, we will prefer to save them in a continuous segment. I'll say block by block. So to make it more efficient in accessing records from the disks. And that is the difference between B tree and binary search tree. A B tree is a search tree, alright, but it's not a binary tree. By the way, there are many versions of B trees. We have the original B tree, and then B plus tree, and also B minus tree. What is introduced here is the B plus tree. And you can check out other forms of B trees if you like. So here's the definition of a B plus tree. First of all, a B plus tree is not necessarily a binary tree. Usually it's not a binary tree. It's a tree of order m. The B plus tree of order m is a tree with the following structural properties. First, the root. The root is either a leaf node or has between 2 and m children. Notice here that we cannot have the structure that we have one root plus one child. That is impossible. Okay, if we have a root node, it must have at least 2 children and no more than m children. And all non-leaf nodes except the root have between half of m and m children. So for any other interior nodes, the minimum number of children will be half of m. And that's the most interesting part. That is, all the leaf nodes are placed at the same depths. So it's perfectly balanced. It's so perfectly balanced because this kind of tree is constructed from bottom up, not from top down. One detail to be noticed is that we also assume that each non-root leaf node also has between half of m and m children. Let's take a look at one specific example to have a better understanding of the structure of a B plus tree. So this is a typical B plus tree of order 4. It's also called 2, 3, 4 tree because each node may have at least 2 children, either 2 or 3 or 4 children. And all the actual data are stored at the leaves. Notice that all the leaf nodes are just blocks, and each block is a continuous segment. And each interior node contains m pointers to the children, plus m minus 1 smallest key values in the subtrees except the first one. What does it mean? Say for example, let's check out what is 25. 25 is the smallest element in its second subtree, where 31 is here, 41 is here. So what is 21 here? 21 is the smallest element in this subtree, and so on and so forth. And all those actual data are stored in sorted order, okay, within each block, and also between the blocks. They are in sorted order. Now let's check out those insertions, deletions, and find by looking at one example. Suppose we now have a B plus tree of order 3, and we have some numbers stored in 5 blocks. Okay, let's group them in this way and try to build the tree from bottom up. Okay, so this is the first level parent nodes. 16 is the smallest number here, and because this subtree is not full, and therefore we have one empty space left in this parent node. And this subtree is already full, so 41 corresponds to the smallest number here, and 58 is this 58. And then let's build the root. So what will be contained in the root? The root has 2 children, so it's not full because the other 3. The root is not full. It must have one empty space plus what? Plus 22, where 22 is the smallest number here, right? So it's 22 plus an open space. Now let's try to find 52. Finding a record is similar to what we do to a binary search tree. Well, let me emphasize again, B tree is still a search tree. It's just not a binary search tree. So what we do is still we start from the root and compare 52 with 22. Say 52 is larger than 22 and there's nothing here, and which means that 52 must be in this branch. Okay, now continue to compare. To compare 52 with 58, it's smaller than 58, so it's not in this block. It's greater than 41, and therefore it must be in this block. And finally, call binary search to find it from this block. This is a very simple example because we are only talking about order 3. If this is not order 3 but order k for some larger k, and then there are going to be how many keys here? K minus 1 keys, right? So in order to find the proper branch of this record, we're going to have to call binary search, right? Call binary search and try to find the proper position for this 52. Okay, that is for finding. And for insertion, let's try to insert 18. What's going to happen? Step 1, let's try to find 18. Okay, since 18 is smaller than 22, it means it must belong to the first branch. Okay, and 18 is larger than 16, so it must belong to this block. And search this block, say 18 is not in, and there's still one space available, and therefore we make the insertion and add 18 here. Next, let's try to insert 1. What's going to happen? Since 1 is smaller than 22, and we follow this branch, and 1 is smaller than 16, and therefore it must be in this block. But this block is already full. So what do we do? A very simple solution would be to make the insertion and then split this node into 2 nodes. But then we have to be careful here, because by splitting this node into 2 nodes, we're adding 1 extra node to its parent. So we have to check if the parent is full or not. In this case, the parent is okay because we still have 1 space available here. So then we can make the insertion and split this node into 2 nodes and then adjust its parent. So now their parent contains 2 keys. 11 from this node and 16 from this node. Alright, now next, let's try to insert 19. So step 1, we try to find the proper position for 19. It comes to this node and realize that this node is full. There's an overflow. But we have to make insertion anyway. So after the insertion, we would like to split the node. But then we have to check its parent. Can this parent node have another extra node? Impossible, because this one is also full. Then what do? We just continue to move up to check its parent. Okay, this one is okay because this node is not full yet. So, which means that we can split this node into two nodes, and which means we can split this node. And therefore, the resulting tree would be like this. Okay. First, we insert 19 into this node and split it into two nodes. And therefore, that will cause an overflow of its parent. So we split the parent into two nodes. One holds the first two children and the other one holds the next two children. And then update their parent. Now as your practice, try to insert 28 by yourself. So I would suggest you to pause the video for a minute and try to solve this one, and then we're going to compare the answers. Okay, so first of all, 28 is supposed to be inserted into this block. And then there will be an overflow of this block, an overflow of its parent, and an overflow of the root. And therefore we have to keep splitting. Split this one, and this one, and create a new root. So here's the result. Okay, this one is splitted, and its parent is splitted, and the root is also splitted into two nodes, and a new root is generated. Okay, let's make more trouble. Let's insert 70. So 70 is going to be here, and there will be splitting again. To see that the simple splitting strategy will generate more leaf nodes, and more leaf nodes will result in a higher tree. So another strategy to solve this is, instead of making simple splitting, let's first try to find a sibling which is not full. Try to find a sibling with only two keys and make some adjustment. So to keep more nodes full, so to make the whole tree more compact. However, if you ask me, I myself would prefer to use the simple splitting method. Because what? Because it's really simple. Think about this. When you implement a B plus tree, how are you supposed to find the sibling? And if there are many siblings, how are you supposed to find a sibling which is not full? It's going to be quite complicated. Well, you can say that we can maintain all the siblings in the linked list. Yes, certainly you can do so, but think about the worst case. So what is the worst case? The worst case is when all the blocks are really full. Then you're going to have to check everyone before you make the splitting, right? So why bother? So much about the insertion. Deletion is very simple. Deletion is similar to insertion. It's just a reverse, except that the root will have to be removed when it loses two children. So in general, let's consider a B plus tree of order m for any m. And this is the pseudocode for the insertion with simple splitting. So we're supposed to insert this element x into this B plus tree T. Step 1, we have to try to find the proper block, say the proper leaf node for this x. So we search from root to leaf for x and find the proper leaf node and make the insertion first. And then check if this node has an overflow, if this node has m plus 1 keys. We just split it into two nodes and check its parent. It means that we have to rearrange the keys in its parent. And notice that this is a while loop. If there's an overflow in its parent, we just keep going with the simple splitting. And if the node to be splitted is the root, we're going to have to create a new root with two children. Okay, now before we analyze the complexity of this function, let's first find out the depth of a B plus tree of order m and with n records. So what is it? We'll think this way. If m is 2, if it's a binary tree, it will be a perfectly balanced binary tree, and the height will be log n, right? It will be log n of base 2. Now, this is a tree of order m. In the worst case, what's the worst case? The worst case is that every node has at most half of m children, right? And therefore, the height or the depth will be log n, but not with base 2. It's log n with base half of m. And it can be written as log n over log m. So the base is no longer a constant, but that 1/2 can be ignored. So you can write it as big O of log n over log m. That's the depth of the tree. If we simply look at the expression of this depth, we realize that when m gets larger, this upper bound gets smaller. For fixed n, when we have a larger m, we're going to have a smaller number here, right? So does it mean that we should make m as large as possible? To be extreme, what if we just let m be equal to n? So we're going to have one root plus n nodes. So the height of the tree, or say the depth of the tree, is just 1. Will it be the best case? Wait till we see the overall performance of this insertion. Talking about the complexity of insertion, we have to consider several points. First of all, how are we supposed to know whether or not we're going to have an overflow here? Notice that we're talking about blocks. Basically, it's like an array. So first of all, we have to insert a new element into the array. In the worst case, it's going to be big O of m. So big O of m for each splitting. And therefore, in the worst case, we're going to have to make splitting from bottom up, from the leaf node to the root. And every time it requires big O of m time to make the insertion and check whether or not this node has an overflow. Okay, so the total time will be m times the depth, where the depth is log n over log m. Now you see that m is not only on the denominator but also on the numerator. This function is not a simple decreasing function. When m gets larger, this function might turn into an increasing function eventually. So it's not the case that we should make m as large as possible. And for finding the time complexity of the function, find is just big O of log n, because the time taken to find the record certainly depends on the depth of the tree. But at every interior node, in order to determine the correct branch to go, we're going to call, say, binary search. That is going to take log m time to find the proper branch at each level. And this is the total number of levels. And at each level, there's going to be a log m step to go. So log m on the numerator and denominator will be cancelled out, and only log n is left, which means that the function find is independent of the order of this tree, but only depends on the number of records. So practically speaking, the best choice of m is either 3 or 4.